Hello guys, good morning to all of you. Today in this session we'll be talking about phase transitions. This is one of the most important topics from the thermal and statistical physics. We'll try to cover this topic by today. Before I start, let me know if everything is all right so that we can quickly start our session. Am I audible? Good morning, Vantage Point. Good morning, Harry. Okay, so I think everything is all right. So we are in a position to start today's session. So we'll start with first, what is this phase transition? You know, the best example to give phase transition is the example of water. Water, if you cool it down, it becomes ice, and if you heat it, it becomes vapor. So here you can see three phases: vapor phase, and this liquid phase, and the solid phase. This is primarily concept phase transitions. Now these are the cases. These are the cases for you can say H2O or water. But for some other systems, the phase may be other things. Okay, it may not be water, then ice, then vapor. It may be something else also. We'll talk about them, and based on that we will get two types of phase transition: first order phase transition and second order phase transition. We'll talk about them in detail in today's class. So in phase transition we consider a system whose phases are in equilibrium. In slight variation of external condition means here mainly temperature and pressure. So based on the variation of the temperature and pressure, it results in a certain amount of the substance passing from one phase to another, and this phenomenon is called phase transition. Now the phase transition is best illustrated by this pressure temperature diagram. As you can see in this pressure temperature diagram, these three lines, one is this line, another one is this line, another one is this line. These three lines are used to separate between the solid phase, liquid phase, and vapor phase. If you closely look at, then this portion beyond this, it is your solid phase. This much of area, this is solid phase. Now if you consider this lower portion of this curve, you can see from this to this is your vapor phase. This much of region is vapor phase, and the remaining portion is the liquid phase, means this portion. Okay, now these three things are meeting at some point. This point is called the triple point. I think visibility is more become less clear by drawing this. Okay, you can see these three lines are cutting a point. This point is the triple point and the corresponding temperature you know TTP, and the pressure is PTP, and there is another thing is called critical point, and the corresponding temperature is critical temperature and the corresponding pressure is known as the critical pressure. So let me just make it simplified for you. We'll rewrite this drawing. We'll redraw this curve to make it simpler for you. Okay, we have this pressure temperature curve. Our main focus will be on 2 points. One is the critical point where all the three phases are meeting, and another one is critical point, triple point and critical. Mainly the temperature is important. So we can denote the triple point as T and the critical point as T. And if I consider the phasor corresponding to the triple point, we can call it P. So this region, as I told you, this is your solid, and the below portion is the gaseous state or vapor state, and this region is the liquid state. So if we use different color, that will be better. So let's say this green portion, we call it 1. This one is 3. Now if you can define triple point, you can easily define a triple point. What is triple point? Triple point is the temperature at which all the phases are coexisting. Good morning, Murli. Ajay, where is Ajay? So let's define triple point, the point at which the three phases. This one we consider only for the first order phase transition. We are talking it about the first order phase transition. The point at which three phases of a material coexist in equilibrium is called the triple point. At the triple point, all the phases can exist at the same temperature and pressure. You can imagine it in this way, that this line, if I consider this line is separating the solid phase and the liquid phase. On the other hand, this line is separating the liquid phase and the gaseous phase. Okay, so critical point, you can see where this liquid vapor line ends. This is the critical point, right? And if you draw a dashed line here, you will get the critical pressure. So let us define the critical point. It is the point at which liquid vapor equilibrium line ends. So when it is talking about critical point or triple point, it is talking about the temperature. Okay. mainly about the temperature. So also pressure is involved corresponding to the temperature. So for the critical point, del P upon del V at V is equals to Vc, P is equals to Pc and T is equals to EC, Tc will be there. This is 0. So in a similar manner, d square P by dV square at V is equals to Vc, P is equals to Pc, T is equals to Tc. This will also be 0. Good morning, Ajay. Now, can you tell me the speciality of this critical point? So, let's write few note about this critical point, but I don't have space, right? Okay. Okay. Let's do this. The first note being, you see that at the critical temperature, this is the critical point. Critical point, actually, if you want to denote a point in this PT space, you need to define its temperature and pressure. So critical point means automatically you have to specify both, because if you only specify temperature, then what will happen? It may be here, it may be here. Until and unless you mention the pressure, you are not able to define a point, right? So one thing you write, the critical temperature, the critical temperature is the highest temperature at which a substance can exist as a liquid regardless of the pressure. So, you know, if you apply pressure, it turns into liquid, right? So critical temperature is the highest temperature. So if you maintain that temperature, whatever pressure you apply, you cannot make it to gas. It will remain as liquid. Number 2, the critical pressure is the minimum pressure required to liquefy a gas at the critical temperature. Okay, you can see it is the minimum pressure. You can see you can go beyond it. So you can say the critical pressure is the minimum pressure required to liquefy a gas at critical temperature. So these 2 points, you write it as note. And once it is done, we'll go for some problem. Do this problem. The vapor pressure in millimeter of Hg of a solid at temperature T is expressed by this, and that of the liquid phase is expressed by this. For triple point of the material, the temperature is. For solid, you get this pressure expression. For the liquid phase, you get this pressure expression. So for the triple point, what will be the temperature? E T. Do it quickly. I think you can do it easily. What happens at triple point? Just use that logic. At the triple point, all the phases can exist at the same temperature and pressure. Can exist, and use this. They exist, okay? It's not they have a choice. They must exist. Hurry up, guys. It should take few seconds only. Why is it taking so much time? Tell me the answer. At the triple point, all the phases coexist at the same temperature and pressure. So we can say that ln P, if we calculate for solid, it should be equals to ln P at of liquid at the critical temperature, at the critical triple point. Option A 200. Let's see. 23 minus 3863 by T, 19 minus 3063 by T. The 3863 by T minus 3063 by T, 23 minus 19. We can see this is 800, and this is 4. 800, 4, 200 Kelvin. Let's move on. So, first order phase transition. You know the best way to remember the first order phase transition, you can take the example of this vaporization, sublimation, all of these are first order phase transition. Melting, vaporization, and sublimation. These are the familiar examples, but the most familiar type of first order phase transition. What we have, like when something is melting, something is getting vaporized, what happens at that point? At that point, it remains the system temperature and pressure remain constants, right? Where the temperature and pressure, and pressure remains constant. While the entropy and the volume change. Most familiar first order phase transition. Now, what are the properties of a first order phase transition? Look, we will talk about it later also. For the timing, I am telling you that the order of derivative of G, which is discontinuous in nature, that is the order of the phase transition. So, for if it is first order phase transition, means first order derivative of G will be discontinuous. G is what? G is the Gibbs free energy. So, in first order phase transition, Gibbs free energy that is G, which is a function of T and P, is continuous. So, note it down. Okay, note it down in mind, not on paper. I will tell you again. So, when I will tell then we will write. For the timing, you just know the order of Gibbs free energy G, which is discontinuous, that will decide the order of the phase transition, and the lower order will remain continuous. You see, for first order phase transition, the first order derivative of G will be discontinuous, and one order lower than that, that is Gibbs free energy, it is continuous. So, for second order phase transition, which will be discontinuous, d square G by dt square or dp square, whatever it is. The second order phase transition, the second order derivative of G will be discontinuous. Obviously, the first order derivative will be continuous in second order phase transition. Okay, don't get confused. Just know it. We'll talk about it later. Don't need to take stress. But their first order derivatives changes discontinuous. G is a function of T and P. So, first order derivative when you talk about, so it may be del G by del T or it may be del G by del P. Okay. So, when you take the derivative del G by del T, keeping P constant, that thing is called molar entropy with a negative sign. This S is the molar entropy, while the entropy and the volume changes. So next you will get volume. This is del G by del P at constant T. It is positive. Okay, this S is known as molar entropy, entropy per mole, molar entropy, and the V is known as molar volume. Here we have used S to be small, okay, but it is difficult to identify small s and capital S, but you consider it to be small s. V is small v. Molar, to denote it, molar entropy and molar volume. In normal entropy, to denote entropy, we used capital S, and to denote volume, we have used capital V, but to denote molar entropy and molar volume, we will use small letters. Sorry guys. Is it done? Now, how this thing coming? S is equals to this and V is equals to this. Can you prove it? Of course you can, because you have done thermodynamic potential. So remember this: volume, entropy, and another thing, magnetization. Are discontinuous in the first order phase transition. I don't know why this mouse stops working. Just a moment. Look, if you remember what we have done in the thermodynamic potential, we made a table like this. It had four things: U, F, G, H, right? F is the Helmholtz free energy, U, F, G, H. So if you go along this direction, what we had? And if you go along this direction, what happens? So along this direction, it is minus Ts. In the downward direction, we have plus PV. And we obtained various relations like F is equals to, we got U minus Ts, H equals to U plus PV. Okay. Then we had G is equals to H minus Ts, and G is equals to F plus PV. Okay, so F we denoted by A, right? We have taken an alternative symbol for F, that is A. So this is same as A is equals to U minus Ts. Okay, and ultimately G is equals to, you see, A plus PV. A plus PV. Let's keep that. Let's take that thing. G is equals to A plus PV. So this is equals to U minus PS plus PV. We have got this, right? Or just keep it like G is equals to A plus PV. So from here we got dG is equals to dA plus PdV plus VdP. Now what is dA? We have already got it, minus PdV minus SDT plus mu dN. We have also talked about it in the canonical ensemble, plus PdV plus VdP. Now this PdP getting cancelled, you are left with VdP minus SDT plus mu dN, and from this we get the molar volume formula, that is del G upon del P at constant T, and we got S because of this minus sign. We are getting a minus del G upon del T at constant T. In addition to it, let me just give you an additional formula, that is the magnetization formula. Magnetization is also discontinuous for the first order temperature, first order phase transition. So magnetization is denoted by M. You can write it in terms of minus del G by del H. H is the magnetic field. Now when you draw graphs related to this phase transition, we will have to draw it in this way, that we have something called the initial phase and the final phase, and we have to show how it is changing from initial phase to final phase. Is it changing continuously, or is it changing discontinuously, or how is it changing? That is why what we do. So in the first para, what we have told you that in the properties of the phase transition, what I have told, Gibbs free energy is continuous, but the first order derivatives like S and V, they are discontinuous. So let us try to draw them, few important plots of first order phase transition. Firstly, we will be drawing the Gibbs free energy. Gibbs free energy is what? It is continuous, right? So we are plotting G. Look, G is a function of T and P. So we may have variation with temperature and also with pressure, right? We need to have two curves to show the variation of G with respect to temperature and pressure. Actually, in Gibbs free energy, let's say temperature is sufficient if you want to show that if you want to see the variation. So how it varies with temperature? So this is the boundary line which is separating, let's say, the two phases. Initial phase, we are denoting it by phase, let's say I, and we have the final phase that is denoted by F. So here we get a curve. So these curves are like more of qualitative in nature. So the properties should be highlighted. Okay, the scaling and all, it doesn't matter so much. So it is just showing that it is continuous. At the transition point, there is no discontinuity. Okay. Now let's draw the molar volume, let's say V, that is del G upon del P at constant T versus temperature. Okay. So it will also have a separating line. Now initial phase looks like this. So you can see it is discontinuous. This much is the discontinuity. From this to this, this is the discontinuity. Phase I, and this is phase, final phase, phase F. This is a molar volume. And you can see this much is the discontinuity. Now if we plot it for the molar entropy, this one we have plot for molar volume. For molar entropy we have to use this formula, S is equals to minus del G by del T at constant P versus temperature. If you see, then this will be because of the negative sign, the nature will be just opposite of it, like this. This is phase I, this is phase F. Okay, this is the plot for entropy. The specific heat at constant pressure goes to infinity in this type of phase transition. If we draw the variation of Cp with respect to temperature, this is all first order phase transition plotting. So we have the initial phase, will vary like this, phase I, let's say, and at the transition temperature it turns to infinity. At the transition point, okay, it goes to infinity. So we can say that in the first order phase transition, the specific heat diverges. Cp diverges at the transition point. Clear? Can you move forward? Have you drawn it? And guys, don't only rely on the PDF which I will be uploading in the course folder. You should also write during the class. It will be a practice. If you think that I will just see it from the PDF uploaded later on, then that will not be so beneficial. Okay, take PDF just like a backup. Okay, and try to write to maximum in the class itself. during attending the live. That will be more efficient. Or if you are making notes, what you can do, you can while doing the class, you can write it on some rough page and you can make a good note, fresh note in some other note. In that way, one time revision will also be done. So it's up to you. And if you are not drawing this along with me, then it will not be so effective. Let's move on. I hope this is done. Vantage, Ajay, Murli, Harry. Let's go to the Clausius-Clapeyron equation. This is the mathematical equation which governs the first order phase transition. It describes a relationship between the pressure and the temperature, P and T. And if you consider a PT graph, it actually represents the slope of the phase boundary in the PT diagram. This equation is known as this equation is written in this way. This is the most important equation which you have to remember. dP by dt. dP is the change in pressure with change in temperature, dt is equals to L upon T times Vf minus Vi is equals to Sf minus Si divided by Vf minus Vi. L represents latent heat per mole of the phase transition. Vf, Vi are the molar volumes of the initial and of the final and initial phases respectively. And Sf and Si are the molar entropies, corresponding molar entropies. This equation is applicable to first order phase transition. In case of second order phase transition, we will be using Ehrenfest equation. Okay. Where the transition occurs at constant temperature and pressure. This one you must keep in mind. The transition in the first order phase transition occurs at constant temperature and pressure. Here you see Vf and Vi, molar volumes. So specific volume is a term that is given by V is equals to 1 by rho, where rho is the density, specific volume and molar volume. So you can use V is equals to 1 by rho if density is given. If you are not given a specific volume, if you are given density, then you can use this formula V is equals to 1 by rho to calculate this V factor, V term. At the first order phase transition, properties like specific heat, which I have shown you here, specific heat, volume expansion coefficient and isothermal compressibility diverge at the transition point. Okay, so PP is diverging. In a similar manner, two other quantities, two or more, that is volume expansion coefficient, isothermal compressibility. These are the things which also diverge at the transition point, that you keep in mind. So this is the main formula, dP by dt is equals to L by T into Vf minus Vy, and this is equals to, because L is equals to T into Sf minus Si. You can get to know from here that L is equals to T times Sf minus Si. Actually, you should write this thing small, okay? Small s. Here it is small v, not capital V, small v. Just rectify this one. Chalo, let's do this problem. Consider the transition of a liquid water to steam as water boils at temperature 100 degrees centigrade under a pressure of 1 atm. Which one of the following quantity does not change discontinuously at the transition? Very good question. Came in June 2011. Give it a try. Simple question. Option A, gives free energy. Yes, so simple. Entropy changes discontinuously, that you know. Specific volume, that you know. How internal energy changes discontinuously. This the options A, C and D we have talked about while discussing the theory. What about the internal energy? How internal energy is discontinuous? Look, we are specifically talking about the internal energy. Internal energy, you can, if you look at the table UFGH, internal energy, you can see it is G plus Ts minus PV. Okay, H equals to U plus PV, right? So from here, U is equals to H minus PV, H is equals to G plus, yes, we need to correlate G, okay, and S. So that is why we are using this formula. So now look at it. U is equals to G plus Ts minus PV. So from this, can you conclude that U is discontinuous? Now obviously look, G is continuous. T doesn't matter. S is discontinuous. P is like a scaling factor, but this is discontinuous. If some discontinuity is added, the overall function will be discontinuous, right? Because to make continuous, everything must be continuous. No? If something is rough, you can say, oh, the overall thing is rough. U is also discontinuous. Okay? Mathematically. You can imagine it in this way. You can say that G term is also there, it is continuous. Why the overall expression is not continuous? It is like you have made a smooth floor, okay, and a cat just touch one portion of the floor, okay. You have just made it from the cement, and the cat made it very smooth, like 90% is smooth. A cat just run over on some portion. Will you say it is continuous? No, it is discontinuous. Understood? To be continuous, it be totally continuous. Let's move on to the next question. Do this one. Water freezes at 0 degree centigrade at atmospheric pressure of 1.01 10 to the 5 Pascal. The densities of water and ice at this temperature is 1000 kg per meter cube, 934 kg per meter cube. Look, this here density means rho values given. I have already warned you to keep a note on this. V is equals to 1 upon rho. This formula will be useful here. Rho is given, from that you can calculate V, the molar volume. Latent heat of fusion, L value is given. Pressure required for depressing the melting temperature of ice by 10 degrees centigrade, means dt is given to you, dt is 10. Okay, pressure required means P you have to find out. Okay, so can you do this? You can use Clausius-Clapeyron equation. Actually, dP you need to find out. Do it quickly. Could you solve this problem? Look at it. Here we have to utilize the Clausius-Clapeyron equation dP by dt is equals to L by T times Vf minus Vi. This is the formula we know. Okay, L is the latent heat of fusion. Vf minus Vi is a change in volume. So, and to find out what is happening water to ice. So, if you decrease the melting point, what are you trying to do? Look, let's calculate a specific volume, molar volume of ice. This is V ice equals to 1 upon rho ice. Okay, and specific volume of water is V water, 1 upon rho water. Can you write it? dP we need to find out. dt is given to you as 10, L is given to you 3.34 10 to the power 5 joule per kg. What is not given? Everything is given. Temperature what will you take? T is equals to 273 Kelvin. 0 degree centigrade, water and ice coexist at 0 degree centigrade. Option B you are getting. Are you sure? This is equals to 1 upon 934 is 1 upon 1000. Do you observe one thing? Density of water is more than density of ice. Eh? Density of water is 1000 kg per meter cube, but density of ice is 934 kg per meter cube. dP L dt divided by T times Vf 1 by rho ice minus 1 by rho. Look, what is the initial phase and what is the final phase? Can you tell me? You are applying pressure for depressing the melting temperature of ice by 10 degrees centigrade. So it is like the initial phase is water, final phase is ice, right? So that is why we have used V ice minus V water. So let's just put the values. 3.34 10 to the power 5 by T, 1 by rho 1 by 934 minus 1 upon 1000. dt is 10. So let's calculate this. What are you getting? One 1.73 into 10 to the power 9 Pascal. So gigapascal is equals to how much? The 10 to the power 8 na? One gigapascal is equals to how much? 10 to the power 9 Pascal na? Don't we need to change dt to Kelvin? Very good question. Can anyone like to answer? This is a genuine question. Murli, Ajay, Harry, tell me what answer you would give to Vantage. Do you need to change dt in Kelvin? Because depressing the melting temperature of ice by 10 degrees centigrade, it has said you in the question, but we have taken 10. Is it correct or is it wrong? What is your opinion? Tell me quickly. Vantage, you also say. What logic? Whatever I have done is correct. Now you say. We have discussed about this thing in the class itself. One giga is equals to 10 to the power 9. So this is matching with option C. don't need to change it dt in Kelvin because change in Kelvin is equal to change in centigrade scale. Yes. So it is not 1 degree Celsius is equals to 1 Kelvin. It is not that. Change in 1 degree C is equals to change in 1 Kelvin. We don't use degree Kelvin. We just write Kelvin. Okay. So just keep in mind when we are talking about change, the change will be same. But if you consider the absolute values, let's say 30 degree centigrade is not equals to 30 Kelvin. Only the change. Very good, Ajay. Let's move on. In the first order phase transition at the transition temperature, specific heat of the system. Tell me quickly. We have already talked about it. It should be like whatever form questions come, you should be able to do it efficiently. A, B, C, D. Quickly, guys, tell me. Why is it taking time? Option B. Very good. Divergence diverges and its entropy has a finite discontinuity. Everybody agrees? So you need to read all the options very carefully, otherwise you may make mistake. Yes, let's move on to the next problem. For vaporization, among the following, which option is correct? Entropy and a specific heat at constant pressure or discontinuous at transition point. Yes, Vantage, Ajay. Tell me quickly this one. Entropy and isothermal compressibility are discontinuous at transition point. Entropy, specific heat at constant pressure, and isothermal compressibility are discontinuous at transition point. Specific heat at constant pressure, which is talking about Cp. Isothermal compressibility, kappa T. Specific heat at constant pressure, Cp, isothermal compressibility, kappa T, and coefficient of volume expansion at constant pressure all are infinite at transition point. I think we have also discussed the relevant theory. I think you will be able to answer it. Option D, specific heat at constant pressure, isothermal compressibility, and coefficient of volume expansion at constant pressure. So this is sometimes denoted by alpha. These are all infinite at transition temperature. Okay, so don't get confused with this infinite and discontinuous. Discontinuous we have only for entropy and specific volume. Okay, molar entropy, molar volume, entropy and volume. For Cp, isothermal compressibility and coefficient of volume expansion, they becomes infinite. As you try to go from one phase to other phase, it becomes infinite at the transition point. So let me give you a refined explanation of this question. Vaporization is a first order phase transition. During such a transition, the pressure and temperature remain constant. As a result, thermodynamic quantities like specific heat at constant pressure Cp, coefficient of volume expansion alpha, and isothermal compressibility kappa T becomes infinite at the transition point. Harry, are you there? Harry is not responding today. Okay, let's try to understand a very important thing. This part of the theory. From this part of the theory, you get good number of questions. Let's say we are having a first order phase transition. we are considering that a solid is turning into a liquid. Solid is turning into a liquid. This is a phase change. Let's say the volume of solid is V2 and volume of liquid is V3. So obviously, volume of liquid will be much more if you consider the volume of solid. Now we know the Clausius-Clapeyron equation. dP by dt, this is equals to L. What is happening here? Solid is turning into liquid. What is this process called? What is this process called? Solid turning into liquid. It is called melting, right? But if I, let's say, direct from solid to by avoiding the liquid, if it goes directly to, let's say, vapor, solid to vapor, then this equation rightly holds. V2 to V3, the V3 is much greater than V2. The volume of gas is much more than the volume of solid. What is this process called? Solid to vapor? Urdhpatan, na? Sublimation. Yes. Sublimation. So L sublimation divided by T times V3 final volume minus initial volume. Can you write it? Yes, sublimation. Now V3 is much greater than V2. So we can write L sublimation divided by T times V3. Okay. Now you know PV is equals to nRT. So if I apply P, pressure, times V3 is equals to RT, we can write. So L sublimation divided by V3 is equals to, you can see RT by P. So T times V3 is RT by P. And this is equals to L sublimation divided by R P square. Now this is the modified form of Clausius-Clapeyron equation for this case. This is a very important formula. You can actually derive this. This will take few seconds. So you don't need to remember it separately, but you can just quickly derive it. So in your examination, if you are given some expression of the L sublimation, then you can use this formula. Let's say, suppose L is varying in this way, A plus B root T. In this way, L sublimation is varying. So what you will write? You will write dP upon dt. Okay. dP upon dt is equals to L sublimation. Achha, we have somehow missed P. And you also did not notice. Look, dp by dt is equals to L sublimation into P. L sublimation is A plus B root T into P divided by R T square. So we can say dp upon P is equals to A plus B root T divided by R T square dt. So if I take integration on both sides, then what you get, dp by p is ln p, A by RT square dt. So it is minus 1 by R, let's say we are taking common, A by T will come, and you see this B T to the power half minus 2, minus 3 by 2. So this will come out to be minus 2B by T to the power half. So minus we have taken, so it becomes plus some constant. So if you consider that at P is equals to PC, T is equals to TC, the critical point, we can write that ln PC is equals to 1 by R minus A by TC minus 2B by TC to the power half plus. So in this way you can proceed with the calculation. Depending on the type of problem you will be given, you can proceed it in this way. Yes, Murli, we have added P. So this one we calculated with A plus B root 2. Let's take this problem. We will understand it anyways. In the phase transition from liquid state to vapor state, the heat of vaporization is L is equals to A minus BT, where A, B are greater than 0 constants. Assume that the gas behave nearly ideal, means you can use PV is equals to nRT formula. If the critical pressure at critical temperature Tc is Pc, then pressure of liquid when temperature Tc by 2 is given by. The critical pressure, critical temperature is Pc, then the pressure of the liquid, and the pressure of the liquid when the temperature is divided. Look, comma makes many difference. You need to give commas at appropriate positions, otherwise it will completely change the meaning. You must have seen many memes. Hurry up, guys. Do quickly, as quick as possible. Not getting it solved? It's a simple question, guys. What are you doing? You have to increase your speed, guys. Look, dp upon dt is equals to L upon T times Vg minus VL. You can also write it in. Okay, they have used capital L. Let's also use capital L. So it is approximately T times Vg, because the volume of gas is much more than the volume of liquid. Look, here we have done the calculation for solid vapor. Here liquid vapor is also works equally finely. So we can say that dp by dt is equals to P is equals to RT by V. V is equals to RT by P. So L times P divided by R T square. Okay. So let's take the integration on both sides by separating the variables. dp by P, L by R 1 by T square dt. Let's put the value of L, because that is dependent on temperature, A minus BT. Okay, let's put it here. 1 by R times A by T square minus B by T dt integration. Now what does this limit says? Critical pressure at Tc is Pc. So when the pressure of the liquid, what will be the pressure of the liquid when the temperature is Tc by 2? So temperature is going from Tc to Tc by 2. Okay, so the limit will be Tc to Tc by 2. We had the pressure, we need to find out the new critical pressure P. Let's say that is P. So this one will give you ln P by Pc. Now 1 by R integration of A by T square, so minus 2A by T. This one minus plus B by, acha, this is B ln T, na, minus plus Q. dt by T is ln T, integration is ln T, so B ln T. Integration goes from Tc to Tc by 2. So 1 by R minus 2A, you have to put the limit Tc by 2 first. So Tc by 2 minus B ln Tc by 2 minus plus 2A by Tc minus plus B ln Tc. Is it okay, guys? This one 1 by R minus, what are you getting? 2A by Tc, and here is minus 4A by Tc. Minus 4A plus 2A, so minus 2A by Tc. And you see minus B ln Tc is cancelling, minus plus B ln 2 is remaining. And then we can write P is equals to Pc exponential, if I take this minus outside, 1 by R 2a by Tc minus p ln q. That exactly matches with option D. Tell me if you have understood or not. Can you move forward, guys? Have you done it? If you have done it, let's do this. Liquid helium has a normal boiling point of 4.2 Kelvin. At a pressure of 1 mm of Hg, it boils at 1.2 Kelvin. Estimate the average latent heat of vaporization for helium in this temperature range. This is also a nice question. Normal boiling point is given to you 4.2 Kelvin. At a pressure of 1 millimeter of Hg, it boils at 1.2 Kelvin. Normal boiling point. So what is the normal pressure corresponding to this normal boiling point? In millimeter of Hg, if you consider, look, the final pressure is given in millimeter of Hg. So this is 760 millimeter of Hg, right? So P1 is like 760 millimeter of Hg, P2 is 1 millimeter of Hg, it's T1 we can say, and this is T2. So you have to find an average latent heat of vaporization, means L vaporization you have to find out. Will you not be able to do it? Everything is given. You just need to decode whatever thing is given in the question. Once you are able to decode the quantities which are given to you and what quantity you need to find out, and if you know the formula, you can put them into the formula, then you will get the answer. Simple. The gap between an unsolved problem and a solved problem is the art of decoding. The more efficiently you decode the question, the more efficiently you answer the question and get good marks. So here also we will be utilizing that approximate form of Clausius-Clapeyron equation. Yes, so we will be utilizing dP upon dt is equals to L vaporization divided by RT square multiplied by P. Okay. Now we have to find out this L vaporization. So what you can do, you can take this dP by P as usual. This is equals to 1 by R dt upon square. And average latent, it means it is talking about that it remains almost constant. So we can just take this L vaporization to be a constant quantity, keeping it with R. So this is Ln. Now let's say the pressure is going from P1 to P2 and temperature is, let's say, T1 to T2. So this will give you Ln P2 by P1. This is equals to L vaporization by R minus 1 by T, right? T1 to T2. So from this you can get the value of L vaporization. L vaporization is equals to R times this Ln P2 by P1, okay, divided by this minus 1 by T2 minus minus plus 1 by T1. So we can write it 1 by T1 minus 1 by T2. So this is the formula. The value of R we know 8.314 Ln. P2 is 1 millimeter of Hg and P1 is 760 millimeter of Hg. Both are, we are using same unit and they are in the ratio, so unit doesn't matter. 1 upon T1 is 1 by 4.2 minus 1 by 1.2. So whatever value we will get, that is the answer. Let's calculate it using calculator. I'm getting 92.658. And what will be its unit? It will be in joule per mole. Is it clear, guys? Tell me quickly. Okay, let's go on to this problem. A vapor liquid coexistence curve is given by Clausius-Clapeyron equation. Q is the heat of vaporization per particle. Assume that vapor follows the ideal gas law and has density which is much less than that of the liquid. Then relation between pressure and temperature T is given by. This is also a simple problem. Do it quickly within few minutes. Vapor liquid coexistence curve is given by Clausius-Clapeyron equation. Vapor follows ideal gas law. The relation between pressure and temperature you need to find out. So let's start with the Clausius-Clapeyron equation. dP upon dt is equals to Q is the heat of vaporization per particle, really latent heat of vaporization. So Q by T times volume of vapor minus volume of liquid. Now you know volume of vapor is much greater than volume of liquid, so we can write that dP by dt is equals to Q times PVV approximately. Now since PVV is equals to KT, because vapor follows ideal gas law, we can write volume of vapor is KT upon P. This is not rho, this is P for pressure. dP upon dt is equals to Q P by KT square. Same thing, you see, it may come in different forms, actually it is the same thing. रिश्ता वही, सोच नहीं गाइज. Option A. Tell me if it is clear or not. Hurry up guys, we do not have all day. This came in June 2015. The condition for the liquid vapor phase of the fluid of a fluid to be in equilibrium is given by the approximate equation dP by dt is equals to QL by TVP. This is the Clausius-Clapeyron equation. So the equation is already given to you, okay, the short form. But where is P? Don't you think Q is equals to ml? Volume per particle in the vapor phase, Q is the latent heat which may be taken to be a constant. Don't you think a P is missing here? No, actually they did not put the value of V. Okay. QL by TVP, that is okay. If the vapor obeys ideal gas law, which of the following plots is correct? So we need to have the graph between ln P and T. So from this we can find out the expression of ln P and see what kind of graph we are getting. So what is given to us? We are given dP upon dt approximately QL by T V P or V average P, V VAP, V VAP for ideal gas. PV is equals to RT because the vapor obeys ideal gas law, so we can peacefully apply PV is equals to RT, and hence dP by dt becomes QL by T times, okay, so V VAP is equals to RT by P, so RT square, and P is going up, and once again same calculation, QL by R integration dt by T square. Why not integration on this side? So let's say initial pressure is P naught, final pressure is P, initial temperature is T naught, final temperature is T. So the left hand side will give you ln P upon P naught. What about the right hand side? QL upon R minus 1 upon T naught T. So we can say that ln P minus ln P naught is equals to QL by R. Let's take this T naught first, then this minus will be absorbed. So 1 upon T naught minus 1 upon T. And that gives us ln P is equals to some constant ln P naught plus QL by R T naught. This is constant, these two terms which we have just written, these two terms are constant, minus, you see, QL by R times 1 upon T. So we have to see the change between ln P and T. This is what we have. Okay, we need to focus on ln P versus T. Okay, if it had given you 1 by T, then you would have got a straight line, okay, with negative slope, but it is asking about the T. So which option is correct, guys? So we can check at different points. What are the points we can check? One point we can check that we can check the behavior at T equals to 0. You see the behavior of T equals to 0 is different. We can check the behavior at T equals to infinity, that is also different, and we can have a rough check in between 0 and infinity. So if we apply these three tests, then the correct option will come out. So first of all, as T tends to 0, let's consider the first check as T tends to 0. You see ln P, if you put T equals to 0, this part is some positive constant, right? Some positive constant minus infinity. So we can say it is going towards minus infinity. So look at the options. This is going towards minus infinity. Okay, this is going towards plus infinity, so option B is discarded. this is going to negative infinity, this is also going towards negative infinity. So we have just removed one option. Now let's apply our second logic. As t tends to infinity, what will be your ln p? Ln p, this first part is positive constant, so we don't have to bother about it. 1 by infinity 0, so minus 0, so you should get a positive constant, right? Some positive finite value, so option C is matching. Option A is discarded again because it is giving negative value. Option D is also a potential candidate because it is also giving you a positive value at t equals to infinity. Okay, so we have to now remove one of the options from these two. If you consider for 0 less than t less than infinity, in this in between, what is the slope? Slope of this curve ln p versus t. Slope is positive. If slope is positive, you see, slope means it is basically determined from the tangent value. Tangent is the angle, tangent of the angle made by the slope with the x-axis. So if you consider this curve, you see the tangent, you will get a theta value. So tan of theta, that will be positive. Okay, for here it is positive. But if you consider this, let's say drawing a tangent here, somewhere here, so the angle is obtuse angle, more than 90 degrees. So that will give you negative value of the slope. So option C is the correct option. Is it understood? Any question? If you ask, then I will explain. Tell me quiz. The last point, have anyone understood? Has anyone understood the last point? Vantage, Murli, Ajay, could you understand the last point, how the slope is positive? So it's a simple thing. Slope, how do you represent slope? Dy by dx, right? This is the slope in the y versus x curve. In a similar manner, if you want to calculate the slope between the curve ln p and t, if you calculate d ln p by dt, so you see this minus sign will be absorbed, and this is positive constant, so that is not that will be 0. So ql by r 1 by t square dt. So this is positive. This is the slope. The dt will not come because taking the total derivative. This is the slope, and which is positive. Slope you understand now, everybody? If you have, let's say, y versus x curve, if you have a curve like this. What is the slope? Let's say at this point, what do? We draw a tangent and see how much angle it makes with x-axis. Then tan theta, it is the slope, and it is also, let's say this point is xy. The slope, you see at each and every point slope will be different. The slope is dy by dx at, let's say, xy, and this is represented by tan theta. Now if you consider a straight line, there will be only one slope. Okay, now if you consider y versus x, if you consider y equals to mx curve, okay, y is equals to mx, how many slopes you will get? You will get one slope. Whatever you go, wherever you go, it will all be, let's say, same value of theta 45, let's say y equals to mx. Whether you take this one, at any point, if you draw the tangent, you will get same angle. So that is, slope is constant. But for a curve like this, if you draw a tangent here, you will get a tangent, let's say, like this. If you draw a tangent at this point, so you will get like this. So the angle will change, and as a result, the slope will change. I think now everything is all clear. Tell me, guys. Okay, let's quickly go for second order phase transition. Although you see most of the questions remains from the first order phase transition, but it is our duty, moral duty, to cover the second order phase transitions also. Let's talk about it a little bit. Here Gibbs free energy and its first derivatives are continuous. As I told you, second order phase transition means second order of the Gibbs free energy will be discontinuous. So the first Gibbs free energy and its first order derivatives are continuous, but the second order derivatives are discontinuous at transition point. Ehrenfest defined the order of transition as the order of the lowest derivative of Gibbs energy that shows a discontinuity at transition. In this transition, entropy, volume, magnetization, density changes continuously. In the first order, they were changing discontinuously, but in second order, they will change continuously. Cp, coefficient of thermal expansion, isothermal compressibility, change discontinuously. Okay, so you notice difference. Okay, chi m is equals to del m by del t equals to minus del square g by del t square. This is the second order derivative of g, so they will change discontinuously, but chi e, this changes discontinuously. Chi e for electric, m for magnetic. Chi m is the magnetic susceptibility, chi is the electric susceptibility. This PDF I will share in the course folder, so don't worry. Let's quickly move on. These are the plots. Gibbs free energy, you see, G versus T, G versus P. These are continuous. Okay, Gibbs function. These are continuous. First derivative, you see, S is equals to minus del T by P versus T. So this one, for first order phase transition, we have seen that there were discontinuity, but it is a second order phase transition, so it is continuous. Similarly, S is equals to then the variation of entropy pressure, this is also constant, minus sign, this nature is changing. Second order phase transition occurs simultaneously over the entire volume. If you consider, let's say, a ice filled water, you see some portion of the water remains icy, some portion like watery, and as you increase temperature or decrease temperature, the phase transition do not happen simultaneously all over the volume. It happens locally, right? Some portion of the ice melts, some portion of the water gets into ice, like that. But in case of second order phase transition, it occurs simultaneously over the entire volume, which does not change. There is no spatial separation, hence do not coexist in equilibrium. In first order phase transition, we have seen the coexistence of liquid, vapor and solid phase. But here the phase transition happens simultaneously. So either you will get at one time, you will get only one phase. So there is no coexistence of multiple phases. There is no spatial separation, hence do not coexist in equilibrium, unlike the situation that arises in the first order phase transition. I hope you are all getting it. These are some other plots in the second order phase transition. You can see how molar volume change. Remember, this thing gives free energy and its first derivative, like molar volume, molar entropy, they will change continuously. But the second order derivative, they will change discontinuously. Del G del P at constant T versus P, you can see Cp, you see this is discontinuity, this shows discontinuity, initial and final. So this much of discontinuity you have. Alpha T, volume expansivity, this is also discontinuous. You can say this is initial phase, this is final phase. Density of helium 2 and helium 1, you can see. Specific heat, helium 2 and helium 1, there is a discontinuity. So sometimes it asks what is the transition from helium 2 to helium 1, what kind of phase transition it is? It is second order phase transition. Now, what are the mathematical equations which governs this second order phase transition? Phase transition of order higher than the first governing equation is Ehrenfest equation. So two equations are, although these equations are does not come generally, but you have to be prepared well. So for your convenience, I have just mentioned it. dP by dt at constant s equals to Cpt minus Cp1 by T into V into alpha 2 minus alpha, using the constancies of entropy. S1 is equals to S2 at the transition. Cp, what is Cp? T times del S by delta at constant. We specify it at constant pressure. Tds is equals to dE or dq. You have already talked about it. Alpha is equals to 1 by V del V delta at constant P. This is isobaric. P means pressure, constant pressure. So isobaric volume expansivity. dP, this is for entropy. This is for volume. dP dt at constant V, alpha 2 minus alpha 1 by KT2 minus KT1. Okay, KT is the isothermal compressibility. 1 by V del B by del P at constant. So these two relations you need to keep in mind. One is volume expansivity, 1 by V del B by del T at constant P, and for isothermal compressibility, 1 by V del B by del P at constant, just interchange T to P, P to T. Volume expansivity, isobaric means constant pressure, and isothermal means constant temperature. In this way you can remember. Transition from normal conducting state to superconducting state, or transition from paramagnetic to paramagnetic. These are all examples of second order phase transition. Okay, keep it in mind. Normal phase to superconducting phase, or paramagnetic to ferromagnetic. These all are example of second order phase transition. Now there is a slightly important law, Truton's law. What is Truton's law? It states that the entropy of vaporization has almost the same value, about 85 to 88 joule per Kelvin per mole. So here, although we are specifying a range, in the question you may be given the fixed value for various kinds of liquids at their boiling points. Entropy of vaporization has the same value in the order of 85 to 88. L by TB, it is taken to be 88, let's say. L by TB is equals to, T is the boiling temperature, 88 kilojoule per kg per mole Kelvin, or joule per Kelvin per mole. dp by dt is equals to p by RT square into L. We know this one. So p by RT square we are keeping. L is equals to 88 times dV we have put. Now if you take the derivative, this is the normal pressure 1.013 bar to some pressure P, dP by P. TB is the boiling temperature. At this boiling temperature, the pressure is 1.013 bar. If you take this integration, then you get an expression like this. dP by P, so ln P. So from that you will get P, and this we have shown this kind of calculation before also. 88 by R dt by T square, so 1 minus TB by T. So this you have to remember. P is equals to 1.013 exponential 88 by R into 1 minus TB by T bar. It is in bar. At standard temperature and pressure, 1 atm pressure or 1.013 bar. Volume of 1 mole gas, you know, 22.4 liter. We have studied in class 11-12 chemistry. Temperature 0 degree. These are some information I am giving you. 0 degree centigrade to 73 Kelvin approximately. 1 atm pressure is 76 centimeter of Hg, and 1 bar is 10 to the power 5 Pascal. So you need to keep in mind this. What kind of question you can expect from this? That is the last thing we'll do for today. So you have to use this formula. P is equals 1.13 exponential 88 by R into 1 minus TB by T. Bracket close bar. Look, if the boiling point of benzene at 1 atm pressure is 353 Kelvin, what will be the approximate value of vapor pressure of benzene at 303 Kelvin? So we can directly use the formula. Boiling point of benzene and 1 atm pressure. Pressure is given to you 353 Kelvin. Approximate value of pressure of benzene at 303 Kelvin. So this is your TB. This is your P0. You have to find out P, and this is your T. Hai na? So you know the formula. You just need to keep it in, put it in the formula. Pressure 1.013 exponential 88 by R into 1 minus TB by T bar. 1.013 exponential 88 by 8.314, 1 minus TB is 353 by T is 303. We are evaluating it in bar. So let's calculate. (88 by 8.314) 1 minus 353 by 303 exponential of this result into 1.013. I am getting it 0.1766, approximately 0.18 bar. Option 2. Tell me if it is understood or not. Oh, what a busy day. So with this we complete the complete phase transition. On the next class what we'll be doing, I think Ising model or something. I have to check. Okay, so let's end the session here, guys. Thank you very much for joining this session. I hope you find this session useful. If you are new to this channel, please subscribe to the channel and don't forget to press the bell icon. If you are interested in taking the top 100 most important topics course, you want to take it, link is given in the description. Okay, you will get all the PDFs downloadable, but the videos are not downloadable. You can watch it on mobile. laptop, etc. Okay, with this, thank you once again. Bye bye, take care.